So we are ready.
Okay, thanks.
So I will talk about some details about the discovery and study of this WD-CHARM teta quark that we made recently and available on this archive link. Actually, I want to say that the slides were prepared by Mikhasenko, and I just he asked me the last minute to talk with him because he just won't be able to join right now. So firstly, just to remind that some key things about the LHCb, which I think you know pretty well. So the key point is that it's firstly the proton situated in the proton-proton machine and covering the forward region. So therefore it gets the largest sample in the world of the B and C hadrons. And thanks to their excellent tracking system, we get their very, very good momentum and therefore mass resolution. And thanks to the system of the ring image Cherenkov detectors, we got really good identification of the pi and scans of protons. So in the analysis and measurement, which I'm going to talk, we have selected a combination of the D0, and pi plus, where D0 decaying to the K minus pi plus. And in our selection, we require that all the tracks should be good quality, and the vertices of the D0 candidate should be of good quality, and that all the tracks have the large transverse momentum to suppress the combinatorial background, and that all these K-ions will be very well identified. So as there are the pions and K-ions of the same sign in the event, we especially ensure that they don't share the same track. So these candidates are really different particles. After the preselection, we found that the sample is really clean. You can see that by looking at the two-dimensional plot on the left of the slide, which is the mass of the two K-pi combinations there. And you see the huge peak corresponding to the two D0s and almost no background. However, we further suppress it by doing the 2D feed to this distribution. And then we subtract this background contribution using the weights. After we do that, we just plot the mass of the D0, like DD pi combinations, and for the D0, this is the red plot on the bottom. You see the huge peak somewhere near the threshold, so the DD star. And if you look onto the similar plot, which is for the D0 anti-D0 pi plus, which is the blue on the top, there is not such a structure there. Therefore, you can understand that at the peak we see into the D0 pi plus, it's not some artifact or reflection of these charm or anti-charm events. So once we knew that there's something there, we needed to describe the peak, and it was immediately clear that you can't use some typical bright Wigner shapes, because here the threshold is so close to the peak position that you need to account for the opening thresholds for these DD stars, and also you need to account for the finite width for the D stars. So we started to construct the following model, where firstly we assume that the peak we see it's the teta quark, this WD-CHARM teta quark, and it's the ground state. Therefore, as expected from the theory, it should point to numbers 1 plus. And then we assume that it's decaying to firstly D star combinations, and if it's then the D stars decaying to D pi or D gamma. So our second assumption was that the coupling of our teta quark to the both D0 D star plus and D plus D star 0 are the same, and that this because it's the isoscalar and there is no isospin violation in the decay. So after the two assumptions, actually all the matrix element for the decay is fixed, because the consecutive decay of the D star to D pi or D gamma are fixed because of the known quantum numbers and known branching fractions. So once we do this, we want to get the final amplitude for the decay depending on the mass of the d pi combination. And for that, we construct an amplitude in the way which would preserve both unitarity and analyticity. So, and by free, we got accounted for their like effective three-body phase space by actually integrating the matrix element I described in the previous slide for the whole Dalet phase space of the dd pi, and also by ensuring the unitarity, we automatically, like, it means that we basically include all the possible DD scatterings as shown on the left bottom of the slide. Therefore, there are only two parameters in the model domain. This is the mass of the peak and the coupling of the theta quark to the DD star. So once we get this model, we convolve it with a detector resolution, which we determine from simulation, and combined with some smooth two-body phase space function for the background. And here's the result of the feed to data. You see that it describes the peak really well. There is a nice feature on the feed that once your coupling of the theta quark to the DD star gets really big, then it doesn't affect on the shape of the peak anymore. And so the only thing that matters is the mass position of the peak, and just the bare mass, that's what determines the visible width of the peak. Therefore, from the feed we extract the mass, which happens to be 360 kV below the D0 D star plus threshold, and we set the lower limit for the coupling. This slide is just shown how would the distribution of like the signal look like if it wouldn't smear it with the resolution. So you see that in the vicinity of the peak itself, it resembles the Bright-Wigner a lot because it's really very narrow, just slightly below 50 kV, which is actually determined by the width of the D star. It's roughly half of the D star width. However, when you get closer to the firstly D0 D star plus threshold, the shape becomes clearly asymmetric, and you see this in the insert and in the plot. You see how function becomes gets a step-like behavior after passing the first threshold and after passing the second DD star threshold. So okay, that's basically repeats what I was said. So let's go to this slide. As we have the feed, we have the function for the analytic function for the mass shape. We can try to extract the pole position, which is not trivial in this case because of the finite width of the D star, whether still possible. We got the pole position of mass around 360 kV below the threshold, and the width parameter again it's like 48 kV. So in the vicinity of the pole, we can make an expansion of the amplitude, and we can try to match it to the non-relativistic analog. So if we make this matching between this formula of our expansion of our function of the second line with the non-relativistic example in the first line, we can match the terms and therefore extract kind of effective kind of analog of the scattering length, which happened to be -7 Fermi, and analog of this effective range, which in our case happens to be negative. And the only thing we can set is the upper limit for this to be around, the upper limit we set is around 12 or 17 Fermi. From these values, we can also get the Weinberg compositeness. So the 1 minus z to be larger than half, which is kind of consistent with the molecular hypothesis for the DC, if you tell something. So I should tell that once we have constructed this amplitude, we thought that the tetraquark decays to the DD star, we implicitly, just before I will get to the next slide, I should say that as I describe you this extraction of the effective range and the scattering length, actually the Misha has sent a new article to the archive 1 week ago where he has revised this procedure. So please check the link at the bottom of the slide if you want to know more details about this extraction. Okay. Go next. So as I was already starting to say, by constructing the amplitude, we implicitly assume that our tetraquark receives kind of the combination of the D and D star, therefore some kind of the molecular object, and this length parameters which we extract around 7 Fermi kind of confirm that it's really spacious hadron. However, there's always a question that it's quite possible that there is some at least some admixture of the compact part, which you can call the atomic configuration here, and that the two C quarks are really close together, binding in the color anti-triplet, and then attract the anti-U, anti-D D quark as like one heavy quark in the baryon. So there should be some admixture, and it's a question how you can extract this, at least from the scattering parameter that we got here. And I guess that's a topic for the discussion. So if you have good ideas how to constrain it, please say it. So good to go next. As I said, we described the model for the tetraquark decay for the DD pi, and the DD pi mass was described. We extracted the mass of the tetraquark from it. Now we can decide that if the tetraquark decays to the DD star, it should give the reflections in the spectra of D0, D0 if the pi is missing, or D0, D plus if the pi 0 or gamma is missing. Once we have all this actually amplitude for the decay fixed, we can extract what would be our expected shapes for these reflections, and we plot them on top of the data, and we find a perfect agreement. So please note that here on the plots, it's not just like the feet with the flexible shapes. The shapes are really fixed, and the agreement we get, it's quite impressive. And even the relative yields in these two channels are consistent with what we would expect from the model we constructed. Though everything we do is agreement with data, one can still ask, what if this tetraquark is not the isoscalar as we have assumed, but it's the isovector? Rather, in that case, we understand that there should be a doubly charged partner, which would be slightly above the D star threshold, and therefore should give the comparable reflection to the D plus or D plus D0 pi plus combinations. Though we see nothing here, so nothing here of the signal around 100 events, even if it would be light. So that's another argument that the tetraquark recedes indeed isoscalar. Then one can ask yourself what we can do next. We now establish that the doubly charged tetraquark exists for sure. There is a consensus in the theory that the analogous quark doubly with two beauty quarks should also exist, and they would be tightly bound, roughly more than 200 MeV below the threshold. So the question is, what happens for the BC tetraquark? In some models, it says that its binding with respect to the threshold should be slightly larger than binding of the CC case. Whether what is interesting for the BC quark, even if it's only like few tenths of the keV below threshold, it won't be able to decay strongly. Therefore, it would be long-lived, and therefore quite astonishing, produce quite astonishing signature for in the kind of spectroscopy. It will be the first long-lived tetraquark to be observed. So what's our prospect for that? It seems that because it's much harder to reconstruct the BC tetraquark or double beauty tetraquark because of the suppression in the cross sections, and especially the branching fraction of the PDK reconstruction. Whether in the future runs we expect to gather much more data. So in the run 3, which actually it was expected to start this year, but most likely we will start collecting the physical data only 2023. We expect almost 5 times larger statistics to be gathered, so that will bring a real chance to observe the next members of this doubly heavy tetraquarks family. So I think that was the last slide. Yeah. So that was the last slide. So thanks for attention. Please stay tuned.
Okay, thanks a lot, Ivan, for this very nice summary. So let's see if we have question. Christoph, please.
Indeed, thank you very much for this very nice talk. Actually, I have 2 questions. Can you go to page 4, please?
Yeah.
Yeah. Here you say no isospin. Sorry, I just misread it, so if I don't have a question. You say no isospin violation in the couplings, and I read in the decays. No, then this question is gone. Can you go to page 10? Okay, here you express R just in terms of this 16W over G square. But when I look in the line above this matching, this formula for the a to the minus 1u, in the square bracket, there's this term psi of s minus psi of mu square. Why don't you consider the contribution of this one to the effective range?
Well, I guess there are could be different ways to do this. We just decided to match on this on the imaginary term, and again, it's actually the Misha who was who could tell you much more about this. But I think I would suggest you to check his new article, where I think he exactly revises this matching.
Okay, this is something we can then eventually come back to the
so my answer is that you could do it in different ways. You could concentrate on the first term, you could concentrate on the second, though the result would be comparable. It would be not exactly the same, but still comparable whatever you do. As you can see, basically on the left, on the graph that's shown comparison of these of the real and imaginary terminal amplitude, but the solid lines correspond to our actual amplitude that we have, and the dashed line to this non-resonant model to which we match. And you see that in the region below 0, like between the mass peak position and to 0, they do not match exactly, but more or less. So,
but this is something we need to come back to this in the afternoon's discussion, because it's this psi term that has the potential of turning R positive. And the sign of R will be, I think, a centerpiece of our discussion later today. But I'm sure that Luciano will come back to that.
Yeah.
Thank you very much. That's all I want.
Yeah, I'm sure that you have a much more extensive point than just what we have done, and I'm sure that it's can be done. There might be more correct way to do this. But,
okay, thanks. So, yeah, sorry. Yeah, and we have another question from Eulogio, I think.
Yes, I mean, without going away from this, I mean, slide, I presume you use, I mean, the standard Weinberg compositeness conditions to calculate the Z. You see, I mean, it would be nice, I mean, to look at it from the new perspective. You know, Dai Lianrong, Jing Zhong, and myself wrote a recent paper on which we improve on the Weinberg condition in order to find out, I mean, the compositeness. And Miguel Albaladejo and Juan Nieves have also another even more recent paper in which they also offer an alternative. Both improve on the formulas given by Weinberg. And now, I mean, another comment, because I thought you said there that you wanted to have a D star plus D0 molecule because this is closer to threshold, the state is closer to this threshold. You know, I mean, it is true that if you calculate the probability, I mean, to find that state, you will find it bigger than the other, than the D star 0 D plus. But you know, what matters in reactions is not, I mean, the probability, but essentially in these processes, the wave function at the origin. The wave function at the origin is given roughly, I mean, it's the G function, loop function times the coupling. So, you know, and that's why you are so lucky, I mean, to differentiate between the isospin 0 and the isospin 1. I mean, so, I mean, more important than the probability is just the couplings or the wave function at the origin. And in this sense, I mean, you should talk rather about the molecule of D star plus D0, D star 0, D plus. I think that's better to talk in these terms.
Yeah, maybe like if, yeah, first I good enough.
Good.
When I was just talking about the molecule, I wanted to not distinguish between the D0, D star plus, or D star 0, D plus, but just compare that there could be a molecule or could be a compact thing. And
yes, yeah. Good. I understand. Yeah,
and just a question what the compact thing is and how much it contributes. That's basically a question for us.
Very good. Thanks.
Thank you.
Okay, thanks. And then we have the last question from Sasha.
Congratulations for great discovery and for a nice talk. Well, naive question from my side. The bottom charm tetra quark, I don't know whether this, I mean, I just wonder about the prospects. Is that at all feasible, you think, to discover next like 5 years? Maybe we will discuss this in the discussion session, but maybe.
Well, my understanding that it's extremely hard to do, though, like there is a chance to do it like once we collect all around 3 data, though it would be much harder than to discover this doubly charmed network.
I know for the doubly bottom, the prospects are really not good, but for bottom charm, well, right, bottom charm baryons have not been discovered yet, or
yeah, they have not been discovered yet, but I think there is still a chance that they will be discovered if you combine several channels in the run 1 and run 2, and I think they will be certainly discovered once you start run 3. And then for this tetra quark, I think you have some not big chance, but some reasonable chance if you combine several modes. Like if you combine 10 modes, then it might be possible, but it's quite a challenge.
Is there some published work on these prospects where we can look for?
No, there's nothing published.
Yeah, okay. Well, thanks so much.
Thank you.
Okay, thanks. And I think we can go for the next presentation by Luciano. Thanks again, Ivan, for this very nice talk.
Thank you. Oh, sorry, I need to stop share.
Yes, thanks.
I forgot.